Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a look at x86 assembly language advanced procedures. They call it advanced procedures, but this is the true one way that C++ actually converts its, and C and C++ converts functions into assembly language and then into machine language. So this busy slide kind of says a lot of what we're going to be doing here in this chapter or in this video. So there's a thing called a stack frame or an activation record, and essentially, like you say, like we don't think about it, right? We always talk about the heap versus the stack, and we never think about it otherwise, right? But there's a whole ton going on whenever we call a function, whenever we pass parameters, whenever we have local variables, all sorts of things going on. There is a lot being maintained for us under the hood that we don't even think about. So every program has this stack, and the stack is truly what you think of when you think of a stack of information, like a stack of plates. But a stack data structure is a lot different than the stack when it comes to the call time stack, because in the call time stack, we can actually go outside of the top, like the top. We can do something other than that. So we can, like, as long as we have access to a pointer, we can go plus or minus, and we're going to see we can go plus and to go into parameter passing, and we can go minus into local variables. So all of this, you're going to see return addresses, parameters, local variables, saved registers. All this stuff is going to be pushed and popped on the stack. So my previous lectures and everything I've been trying to get you guys to do is to try, many of you are using still to this day global variables inside of your functions, and that's a bad thing. And what is the other thing that you guys do that I need to work with you, and to push and pop back the registers, because our contract always is when we create a function, when we return from that function, every other register that I promise not to blow out, EAX usually gets blown out because you usually return something, but everything else gets put back in its place when it's done. So those two things are huge when it comes to setting everything up and making sure that all the registers, all the variables, everything is put into a correct position, and you get the correct result from what the function is supposed to do. So we're going to see this, this video, there's an hour-long video following this one to finish up the course about just going through and just doing this over and over and over again, just to get used to the, what am I going to do? How am I going to do all this stuff? So what now we do, so back in the day, we'll see in the next slide here, what we used to do is we used to move into EAX a value, move into EBX a register or value, and call multiply. And we do that for the Irvine library, right? We move EDX, we move the offset of text into EDX and blah, blah, blah. But wouldn't it be cooler, or wouldn't it be nicer if we didn't have to worry about all those tiny little details, and I could just worry about pushing specific things on the stack prior to calling the actual function? So like, I don't have to remember any details, like 19 is supposed to go into EAX. Like, well, what if I just put 19 first and then 22 second, and then I just called multiply? That would be a much better way of going about doing things. So so what we do here is in the main function now, this is forevermore now, that you push the parameters instead of moving to registers before you call. You push things to the register, or you push things to the stack before you call. And so in the function itself, so now that we're actually going to be pushing parameters along and pushing them onto the call time stack, that changes what we do in the function itself. It complicates things because now we have more parts to worry about. We have push sections, we have pop sections, we have the code, we have a bunch going on. So anytime, this is what this is saying here, anytime I have parameters passed into a function, I am going to basically play around and modify the EBP register, and then the ESP register is always modified automatically by push and pop operations, so we don't really control that. We do the push and pop, that value is modified automatically for us. So if there are variables, or I'm sorry, if there are parameters being passed along to your function, you always do this where you tinker with the EBP register. It's 2 lines of code. We'll see this in a future slide. And then after you're done with that, then if there are local variables, then you tinker with the ESP register a little bit to make sure that you have space for that. And then after all that hard work, my goodness, right? 5 or 6 different steps here, I can finally go ahead and do the real work, the work that the function is actually supposed to be doing. Okay, so let's see. There are different ways we can pass information to a function, as you guys probably know. Depends on your your experience with which languages is how deep you go with that, generally speaking. So in C++, there are three ways to go about it: value, reference, and pointer. And pretty much every modern language only has one or two, like value or reference. So again, reference and pointer, very similar ideas, not identical ideas. Similar, and at least in C++, reference and pointers are, again, similar, but then the syntax changes just enough to cause issues, but we'll see when we get to that. But we're going to talk about passing by value. So when I'm talking about passing a parameter by value, again, my way of thinking is always to use a copy machine example. So if I'm going to pass like to an absolute value function, and I'm going to pass a 5, and I have a 5 sitting in the main, and I go pass 5 to the function, I go to the copy machine, I get a 5, I copy it, I put a copy of the 5 on the stack, and then I call the function. And since there's a copy, now there's two separate versions of this thing sitting around. One is my master copy, and one is the copy I handed off to the function. So at the end of the day, whatever they do to that value over on their end does not affect me sitting here in main, because they're using their copy, I'm using mine, and you can do it. I don't care. You could never use it. You could blow it out. You could just use it. You do whatever. You could rip it up. I mean, I don't care. I just gave that to you as a reference, a starting reference to start from. So that's the idea of what passing something by value is. You're passing a copy of a piece of data onto the stack. And so push always pushes something onto the stack, obviously, but it's between value and reference types. It's just a matter of what gets copied here. So as you see here, x's and y's, like I push the x and push the y. So this is a legitimate call stack. So one thing you have to get used to here with this chapter 8 style stuff that we're doing here is that a normal stack, we think of a stack of plates, we're fighting physics and we're fighting gravity when it comes to the placement of the stacks. But the reality when it comes to a computer is we're actually starting basically from the ceiling and working our way down to 0. So the memory address starts at whatever, and every time I push onto the stack, I'm actually subtracting from the stack when we're talking about what the value of the ESP register is. And every time I pop back, I'm actually moving up, so I'm actually moving in a positive direction. So it's like we do this in a 180 manner here. So we are working downwards. So I push the 5 onto the stack, I push the 6 onto the stack. The ESP pointer is always pointing to the element at the top of the stack. And so that is, the top of the stack holds the 6 because that's the last thing that got pushed, because it's a stack and not a queue or any kind of other data structures. So again, this is a big deal. We'll see this as we go. Okay, so it's do this as versus a reference idea here, passing arguments by reference. So instead of passing a copy of data, like I say, I'm giving you the real data. And now, so what does that actually mean? So like when I'm actually going ahead and just giving you, it's like, oh, here's my master copy. What I'm actually giving you on the other end is a memory address of where you can find the piece of data. Basically, I'm saying like, maybe instead of saying I have the master copy, I can just go, well, here's where the master copy is located. And so maybe I don't hold it in my hands. Maybe I do. It doesn't matter where it is. I'm giving you directions to where you can find it, and then you can do whatever you need to do with it. And if you change it, oh well, I gave you global access to this thing. You can do whatever you want to do. So as opposed to pushing X and Y earlier, now I'm pushing offsets. So an offset is a pointer to something, right? So that's just giving me the pointer to where the Y is in memory and giving me a pointer to where the X is in memory. And so again, everything's working its way downwards and everything works 4 bytes at a time. So one of the push operation is always 32 bits, 4 bytes of storage. So that's why everything is double word here. And so there's a 4 and a 0, and that just comes back to the fact that the X is stored at the 0 offset when it comes to the data segment, and Y is stored at 4 because it's 4 bytes in, because 0 is where X is, it needs 4 bytes of storage, so 4 is where Y starts. And since I pushed Y onto the stack first, there's a 4 on the stack for the Y and the 0 on the stack for the X. And of course, the difference is, us on our end is in the assembly language, high-level language side, X and Y mean something to us. But at the end of the day, the computer has no understanding of the computer. X and Y is just a placeholder for a data, a memory address, and that's all it's doing is replacing X's and Y's with memory addresses. So it's a huge difference between the two. And so the third thing is we teach this when we're teaching functions and arrays and all that. It's like, you think, what am I passing when I'm passing an array to a function? I'm passing a reference. I'm passing a pointer to the beginning of the contiguous block of memory in which the array is held. So in most languages, raw arrays are not completely copied prior to being passed into a function, meaning an array is generally passed by reference. Vectors in C++ and other data structures might not do that. They might actually make a giant copy of things. If you forget that little tiny ampersand when you're doing this kind of stuff with vectors and whatnot, can cause a huge performance hit. So arrays are passed basically by reference or by pointer. And so you could actually replace the square brackets here with a pointer when it comes to the syntax, and you will see no difference when it comes to the way things work out, when it comes to the way this array fill function would be represented in C++. So what happens is if you have a global array, I can determine its size. And so like I can go back and go, get offset. I can always, do all these other operations to be like, get me the size of this thing. How many elements, how many bytes, how many this, how many that. But in like these cases here, all I'm doing is passing the pointer to the array to this function, a general function that's trying to fill this array with data. I don't know what it is. I mean, it doesn't much matter. But the thing is, I'm passing a pointer. Basically, I'm stripping away all the extra information that comes with it when I do this. And so the array gets passed, the pointer gets passed, but I no longer know if it's a byte, word, double word, what is this thing? What kind of array is this? Like C++ and Java, yeah, you get that information because that's part of the language. But here, raw pointer, void pointer, there's nothing to know. So that's why when we teach this stuff, like at the low level in C++ and all that, we always pass along the size of the array as well, because that information gets lost otherwise. So you always have to pass along a pointer to the array and its size in order to do an operation on a raw, just pure raw array. So that's what this slide is trying to tell you. Here's an example of putting both of these types together, the value types and the reference types. And so at the end of the day, pushing them is easy, but we'll see later on when you go to use these things inside the function, well, the value types are easy because you already have been doing that, but the reference types take at least one extra step for all of this to work. So if I have int A, int reference B, int reference C, int D, and you can see here, so the first parameter I'm just presuming is that I'm pushing is the A, so that's just a number, it's just a value type. This is a reference, so it gets an offset. This is a reference, so it gets an offset, excuse me, and this gets a variable, and so that's good. This all works out. This is A, B, C, and D when we're talking about the call into the function, and you can see how our pushes affect the call stack, or the stack itself. 4, 0, 4, 7. Again, these are the offset values of the x and y's. And again, Z doesn't get it, but doesn't get the 8, even though it should be, right? But no, it gets the 7 because it's passing by value and not by reference. So another thing to notice is, like when it comes to a reference variable, I could not, at least in C++ and all that, I could not push a 4 into the second parameter because you can't push an immediate value into a reference because a reference requires, or pointer requires, a memory address. So there is a mismatch there when it comes to reference versus value type. So references are memory addresses, so you can never pass an immediate value into a reference. So you got to be careful for that. And again, every step of the way here, remember we're going downwards with the stack. Everything's coming down from the ceiling when it comes to passing arguments and using the call stack. So this next slide just shows when I actually go ahead and call the function, everything that I did from the previous slide, all those pushes play a role. But now also when I hit call, the next line of code is, whatever, like the memory address of the next line of code is placed onto the stack. And the reason is when I call function, whatever function is and does whatever it's going to do when it returns back, well, how do we know where to return to? How do we know what the next line of code should be when the function is done? And so I just made up this memory address 5 or F596D. I just made up the number, but this is just to say that when I call a function, the assembler will find whatever the next line of code would be, and that memory address gets thrown onto the stack because that's where the instruction pointer will go when we return back from whence it came. So parameter, 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 and now there is a memory address thrown on top of it for a return. We don't ever directly use this. We kind of indirectly do this when we do a ret later on, but this is just the way things go. And just so you understand then we need this information. All of this information needs to get stored. You're going to see it. I mean, it can be quite a bit of stuff here. So, okay. So there are many different ways that different programming languages can access this information. As you can tell, as you can imagine, the pushes of this stuff, the way the memory address, local variables, all of these things, there are many different ways that programming languages can set up when it comes to their formats and their protocols. So we are going to use the C/C++ methodology. And if we continued on in the book, I think it's chapter 13, way at the end of the book, they show you how you could take your assembly language, object files, you can actually compile down into object files, and you can actually use them in C++, as long as you obey these rules, because that's the rules that C++ obeys when it comes to the implementation of the language. If we agree with that and we follow all the rules and we compile it down exactly the way it's supposed to be, we can make it work. Which means that we could write our own really fast functions and time in and write them in assembly language, and so that we could be really cool. It would be, I think it's really cool when you can do that kind of stuff. So again, we're going to use the C++ way, and so we're going to be using the EBP plus and the EBP minus method. I don't know if there's a true name for it. I guess I don't necessarily care what the methodology is called, but we're going to be using this EBP register basically for everything when it comes to variables, parameters and local variables. So EBP, the name EBP stands for extended base pointer, and so what this truly is an immovable foundation. That's a term for it. It's like it's a place in our memory where we will never move it, and we will be able, from this foundational point, we can pivot and find all the information we need when it comes to local variables or when it comes to the parameters that are passed in. And as long as this EBP does not move inside of our stack frame, we always have a firm foundation to find anything we want, and nothing will ever be modified, nothing will ever change. So coming back here, so this is basically the way you do things if you have a parameter that or at least one parameter passing in. Any number of parameters greater than 0, these two lines of code up at the top, whoa, I don't know what just happened. Okay, yep, these two lines of code go at the top, and these two lines of code go at the bottom. And so you're going to see here, we haven't talked about this, and we're throwing a number on top of this. We'll see this in a minute or two. But you see push EBP, move EBP, comma ESP. And so what we're doing is we're blowing out the EBP register, but we're keeping it so we can put it back to how it was when we're done, right? That's the whole point. Push here, pop here, right before we return out of the function. And the reason for this, of course, is EBP and ESP. These are the pointers for the stack, base pointer, stack pointer. And so we try not to directly use these things. We directly use EBP, but we really never, well, we're actually going to play with that one when we talk about local variables. So we have to really know what we're doing to make this thing work. So everything has to work out perfectly. So you have to make sure that you do things exactly right. So push EBP, move EBP, comma ESP, and you'll see in a slide here, you'll see how it all matches up. You'll get to see the call stack. And so again, push and then pop and then the return, and then we'll see this for a number in a couple slides here as well here. Okay, so the ret, of course, is what returns me back from this function when I'm done. I don't know why this is off center here. Okay, so coming back again, just saying, how do I access this information? And do I have a slide for this? There we go. Oh, that's kind of cool. I didn't even, I made that happen. Anyway, so what you can do here is you can say, okay, I have all the stuff from the previous slide, and now how do I access this information? So let's see, coming back. So where did I push? Nope, I don't have that. Do I have that function? Here we go. The array and the size. The array, the offset to the array got pushed on first, and the size got pushed on second. So what happens is, because the array got the pointer to the array got pushed first, that is the first, that's the top of our stack. And then the size got pushed second, and then the return address got thrown on this when we hit the call, and then this push EBP pushed the old register's value onto the stack. So EBP, and then move EBP comma ESP. ESP always points to the top of the stack. So it's always pointing to the top, so we can always move it one way or the other if we need to push or pop another piece of information. So ESP is pointing to the same place here, EBP is pointing here, and EBP is never going to be modified, because that's why we're making this a rock solid foundation. So if you see this, if every element in my stack is 4 bytes of storage, then that means that to get to the first one of the parameters, I have to move up 2 slots. So to move up 2 slots, I have to move up 8 bytes. And again, we're going upwards because we're going up and not down, as again, the reverse of what you might expect. So EBP plus 8 is basically the last thing that got pushed on the stack, and then you keep on going. So in this case, EBP plus 8 is where my size is located on the stack. EBP plus 12 is where my offset, or the offset to the array, is stored. So this is across the board the way things are going to go. Notice how I take EBP plus something, I do the square bracket so I can dereference it. So what this is saying is go to this memory location, which is where EBP is, plus 8 bytes, and then go there and dereference, which means get the value stored there and put it into ECX. So coming back to our example from a minute ago, 100 we could put into ECX because that's what got pushed down the stack. And then at this location, EBP plus 12 is the offset, the pointer to the array. And that's going to get put into the ESI register. So in this case, let's see, the array function, as long as we pass in that information correctly, we push the array, then we push the size, then we call the function, this will work out perfectly because all of this matches up on our end on the other side. So as long as you pass the correct stuff, ESI is the array, ECX is the size, and now we have everything else. And now here where the cursor is, underneath there is where I can actually do more of the work, because now we're back to where you guys, we were a chapter or 2 ago. Now we have all the information we need to do the real work of filling the array or doing this or adding that or whatever we have to do, whatever the job of the function is. It's just there's a lot of extra overhead. There's no doubt there's a lot of extra overhead here. Okay, so here is another example, but now we're going to kind of put it all together here with when we remove stack parameters as we go. Because now, coming back to our example here, I'm going to add 2 and 4 together, and I'll get a 6, of course, obviously, right? So if I add the 2 numbers together. So if I push a 2 on the stack, I push a 4 on the stack, I call the add function, so the 2 will go on the stack, the 4 will go on the stack, and the return address to wherever the next line of code will be, that gets thrown on the stack as well. So the extended stack pointer is always pointing to the top of the stack. That's where it's pointing when we're ready to call and actually physically move into the add procedure here, function. So then the next step is, okay, push EBP on the stack, whatever the old EBP value is, move EBP to ESP. So now, for this moment, EBP and ESP are pointing to the same memory location. And so, because ESP is the top of the stack and EBP is pointing to whatever ESP is pointing at right at that moment. And so what I can do here is I can say, okay, and so this function is going to return the 6, right? So the EAX register is going to hold the return value. So I can take EBP plus 8. So here's my EBP, here's my plus 4, here's my plus 8. So I can take the 4 and it goes into the EAX register, dereferenced. And so with 4 in there, now I can say, hey, let's go to EBP plus 12 and dereference. So that steals the 2 out of here, copies the 2, and adds the 2 to what's previously in there. And so the EAX register holds 6, which is exactly what we want. So we're done with our work, and now we have to unwind the stack. And so the return and the pop and the return, this is how we basically destroy all of the work here on the stack because we don't need it anymore, because the EAX register is all that matters anymore, and everything else is just kind of can be thrown away or cleaned up. And so what we do here is we don't have to put these values back to anything because they're just going to be given back. The stack is going to unwind and all that information is just going to be lost. So the rule is that we have to maintain registers, but we don't have to maintain any of these variables if we just don't have to do that. So then the next step here, if this is looking like this, the next step is, I'll pop EBP. So the EBP goes off back into EBP, so the EBP is restored because we modified it in the course of our action here. And then now this ret, and now you see this number. So the number is a huge deal. And so when it comes to this, because it's the function's responsibility to give the parameters back and unwind the stack. It's weird because you think maybe you would do it over here in main, you would push call and then do a pop or something like that, or do something to get rid of those, push pop. But in this case, the pushes go on the main side and the pops and the return with this value go over here on the function. So what that means is when I do return 8 in this situation, I'm staring at this guy right here, is that the return takes whatever the top of the stack is and puts that value into the instruction pointer. And that's what we want, because we want the return address for the next line of code to go into the instruction pointer so we know this function is complete and we can move on. So that's perfectly fine, and that's great. But then the 8 means, okay, let me get rid of 8 extra bytes off the stack. And what that means is 2 parameters got pushed in, they're 4 bytes each. That's 8 bytes that got put on the stack. This helps me unwind and get rid of the parameters. So I don't have to do like pop EBP, and then I don't have to have like just pop into some random thing and pop into some random thing that I don't care about, and it helps me get rid of the things without having to worry about the overhead of where did that information go. So pop or return plus 8, and as you can imagine, then because this is if the first pop of this return address is 4 bytes and there's 8 more, 12 is 3 elements, the stack is now empty and EAX is still holding the 6 value, and now we're here and we can do whatever we want. So again, this value matters a ton. It feels weird, but it's totally there to help you when you have parameters. Okay, so here's an example. Here's something the same but different here. So I want to write a function that basically creates a subtraction function. So I want to be able to push 2 parameters on the stack, and I want to be able to subtract one from the other. And so in this case, 30 minus 14, call difference, will get me a positive 16. The EAX register holds the result after we come out of the call, and then I can immediately call write-it to put that 16 right up on the screen for us. So this is how we would do things in main, and we could set everything up. So how would we go about doing this? And here is the way the difference engine would get set up. So you say anytime we have parameters, we got to do these first 2 lines of code. We got to do the push EBP, we got to do the move EBP, ESP. Those are always the first 2. And then we have to unwind on the other end, pop EBP. That takes care of this, this guy here, and then ret. And then again, we pushed 2 parameters on the stack, so we got to remove 2 parameters from the stack, and so it gets an 8. 8 total bytes need to get pushed off or popped off on top of the return statement. Okay, so using the thing, move the first parameter, or if you want to think of it, it's hard to. The 14 got pushed on first. The 30 got pushed on second. I don't have a map here, but I'm saying like if. So thinking about this, again, just draw it out for yourself if you need to, that EBP is EBP. EBP plus 4 is the return address. We never use that. EBP plus 8 is the last parameter that got pushed on the stack. So in that case, that would be our 30. The 30 was the last thing pushed on the stack, so 30 would be moved into the EAX register. And then I would go 1 up from that. So what's above the 30 but the 14 on the stack? EBP plus 12, and say, okay, subtract that off. 30 minus, 14, gets me 16. 16 would be stored in the EAX register. And like we were mentioning, that's all there is to it when it comes to the function is done. We've done our job. And now we got to unwind the stack So that's where, again, the pop EBP to remove this guy, and then return +8 to get us to return back to main, and then also take an extra 8 bytes off of the stack. So this is just repetition, getting used to this. Like over time, just fitting on the slide, I like to kind of separate the bread of the sandwich, if you want to think of it, from the meat, or the sandwich part of the sandwich. And so, like, if it helps you to break it apart so that you can see the different parts, then so be it. It's totally fine. Okay, so moving on now, you can also pass, there's also times you want to pass bytes or shorts, right? So like if you have a bool variable and you want to pass that onto the stack, well, that's only 1 byte. How would we go about doing that? And so the stack, you can only push 32 bits at a time. Technically, you could push 16, but for the simplicity of what we're trying to do here, let's not do any of that. And you can never push 8. So 8 is never a good thing. 16 is if you really know what you're doing, because it says even 16-bit values screw around with the Windows API functions and page faults and data alignment problems and all sorts of things that I do not want to have to fix. So let's just use 32-bit values, but we just have to use the move 0 extension and or the move sign extension operations in order to take something that's a byte or a word and extend it out into a 32-bit value before I push it onto the stack. And I believe, if I remember right, these move operations require a register, so you can't just do it because you just can't do it in a, it makes sense that you can do it in a register but not in RAM. So take value, which is a byte, 0, extend it out into EAX so I can push the whole thing onto the stack. You're never going to use that extra stuff, but that's just how the call stack operates and how the call stack works. So you just have to play by their rules. And the same thing goes, move 0 extensions. This is a signed data type. So number is -43, move the sign extension so that I can extend out -43 into the larger space, and then push the EAX register onto the stack. So that's how you would do things like that if you needed to. Okay, so a couple more things here. Now, so local variables changed a lot here. So everything we were talking about is just getting parameters into our function here. So say so what we're talking about here is +8, +12, and if there were more, +16 and +20, and we'll see an example, I believe, before we call it quits here, about just kind of tying it all together. So again, I've been trying to get you guys away from global variables because of this reason, because now that we can use local variables, it's so much easier now. The startup cost, admittedly, is very high, but at the end of the day, even after what we do here, it's going to be easier because I can start tinkering with these different EBP values, just remembering what's what. And basically the translation starts coming along much quicker, especially if you have something written in C++ already. It becomes an almost one-to-one translation when you go to do this for homework or for your exams and whatnot. Okay, so global variables, we generally don't do this in a modern environment. C++, Java for sure. Python is in that weird little land where some things are global, some things aren't, and some things are, all sorts of weird stuff. But we generally don't do that. But we can't, as I said, we definitely have been doing that nonstop. We've been doing that since day one, since we've been learning about this in this course, global variables in x86 assembly language. So the rules, of course, are local variables are only used inside of the function, or depending on if you want to think about inside of a code block, right? If I have a code block, if something is true, do some code block. If I introduce a local variable inside of that code block, once I hit the closing curly brace, it dies. And what that means is the call stack is being manipulated by the fact that you're closing off functions, you're closing off code blocks. And so it makes sense. If you're unwinding the stack, well, then you can't guarantee the validity of the data stored above whatever the top of the stack is. So it makes sense that you can't access that information anymore. So, there's a very solid reasoning why that works. So storage is released when the function or code block ends. I think I just described that. So because storage comes and goes, right, as your stack is winding, unwinding, and doing all sorts of crazy stuff, because of this reasoning also, the local variable names can have the same names as other variables, globals and whatnot, because they apply directly to the function. And so you can have, so you try not to have a mismatch. You try not to name the same things over and over and over again. Goodness gracious, sorry about that. So, because obviously, and some of you in your homework assignments too, you're like, well, you didn't realize that X was supposed to be local, even though, it's pretty, it's one of those rules where globals get taken over, the scope gets taken over if they're named the same things inside of a function call. So, and obviously, it makes things simpler. We don't want a global variable for everything that we ever use. We want to be able to use the stack and just have it come and go as we please. But for things like recursive functions and multiple execution threads and all sorts of crazy things, we do need to keep these local variables going. Like recursion is a big deal, as we're our function calling another function, calling another function, calling another function. All of these things need to be maintained as the functions are doing their jobs, right? So local variables, I feel like I've talked too much about something that shouldn't need much of a sail. We do it all the time. Let's go ahead and try this. So creating a local variable. So let's see. So the first thing we ever do is worry about the parameter passing. We always take care of that first. Okay, so that's push EBP, move EBP, ESP, pop, ret something. That always comes first. That's still the top and the bottom of the function. And now the secondary stuff here is the local variables. So in this case, I'm staring at this, and what this tells me, sub ESP, 8, it's taking the ESP register, which a moment ago was pointing here at the exact same place EBP was pointing, and it said, let's subtract off 8. And so what that does is it actually fills in and gives me 8 bytes of storage that I can actually use for my function, which means I have 4 bytes apiece. I have 2 local variables staring right at me, which is really awesome, right? So, so I carved the space out of the stack. I just did it, just poof, done. So sub, and remember again, everything's going downward, so it has to be a subtraction. If you go in addition, well, you're blowing out everything you need later on, because oh goodness, right? So you're going to be blowing into your local variables if you go up 8 instead of down 8. So give me 8 bytes of storage, and then okay, so everything we did on previously when it comes to parameter passing was on the plus side, and now everything we do when it comes to local variables is on the minus side, because now ESP is always pointing to the top of the stack. EBP never modifies, and you go EBP plus 8, EBP plus 12, but now saying, okay, take 10 and put it into EBP minus 4. EBP minus 4 goes down here, so the 10 goes into this memory location here, and you do need the D word pointer because it won't know otherwise, because it just knows this is a pointer. It doesn't know if 10 is a byte, word, what, so you have to supply the double word pointer to this to get this in here. And so that holds the 10, and then the same thing goes, put a 20 into EBP minus 8. And so now, if you want to think of it, however you want to name it, if this is X10, that's EBP minus 4 now. And Y, if that's Y is EBP minus 8. So it's a weird name for it, but it's the same exact thing you're used to. Just use, instead of variable names, now you're dealing with EBP pluses and minuses, 8s and 12s and 4s and 8s and all sorts of stuff. And so it really does help if you start writing in C++ so that you can write those names in there. And you'll see, for examples, if not this video, the next video, the final video I have on this, just to show you how I can convert. I took some C++ code, converted it into this, and I named the variables minus 8, minus 4, plus 8. And so it's a lot easier to figure out how to translate this into assembly language. And then when I'm done with everything, just like I have the stuff here, before, like I said, I do this, and then right here, right before this goes the add. If I subtract 8, I gotta add 8 because this will take ESP and it'll bring me back. Then I pop the EBP off. I do my ret plus 8 cleared. Isn't that slick? Like take 8 bytes off, take 2 of these, take the EBP off, pop it off, return, pop this guy off, plus 8, done. 3 operations do all of that work, and it's just completely magic, right? So cool stuff. Okay, so then on top of all of this, here's layer 3 to the push-pop conundrums here. So so this is what we do for parameter passing: the push, the move, the pop, and then the ret, if you want to think of that. I like to put it as part of that just so I can remember it. Remember how many parameters I'm passing, and then fill in the ret. And then check, so if you don't have any parameters, you don't have to do it. But just saying this whole section, yes, you have to. And then if you have local variables, do the subtraction. This tells me there's 2 local variables. And then now, when you do the actual work, get your function actually working, and then figure out if any of the registers outside of EAX or whatever you modified needs to be put back. So this just, I don't know, this is just the actual work, but in this case, I used EBX and ECX to do my job, so I pushed them here, and then I popped them back in reverse order. Everything has to go basically, reverse order. ECX, ECX, EBX, EBX, 8, subtract 8, add 8, push, pop, ret, plus the 2 pushes from the side of main. So that's how this goes. So it's a 3-step process, but this is the absolute last thing you do, because there's no reason to maintain these as you're trying to figure this stuff out. Get it working, and then take it and then go, oh, okay, this is what I used. So there's 3 levels to the pushes and pops now, on top of the actual work of the function. Okay, so here is our last function. So let's tie this all together. So let's create a function that takes in 4 separate parameters. They're all value parameters. We're not going to do anything crazy with references. The next video does at least one problem with references. And so let's just take from this x, a, b, and c. Let's return ax squared plus bx plus c. It's like a quadratic, typical quadratic formula kind of thing. So I kind of already wrote the C++ code for us. So I did my best to simplify things for us. So in C++, if this was C++, I would just do return a times x plus b times x plus c, right? That's all I would do. But the reality is I'm translating this into x86 assembly language, and that one line of C++ code we're going to see, that it could be a one-liner, is going to be, what is the answer? What's the actual work? Boy, that much work, right? So before we get there, so it's quite a bit of work. One line, because that's always what things work. One level of high-level language does not always translate to one level, and almost never actually translates to one line of assembly language code. Okay, so we'll get back to this. So D equals A times X, E equals B times X, and then EAX, the register, the return value is going to be equal to D plus E plus the C value, and then we're going to return that value. So this is a pretty good setup, of simplified setup of what we're going to try to do. So then now pushing the parameters on the stack. So 2 goes first, that's the X. 3 is the A. 1 is the B. C is the -5, and then when I do the call to formula, that return address also gets thrown on the stack. And if you want to do the math, you will find out that you're supposed to get a +9 out of this if you use these values for these parameters. Okay, so let's see what happens pushing forward here. Okay, so coming back, the first step is thinking out at least the first steps of the pushes and the pops, at least the first 2 levels, the local variables and the parameters. So there's a push and a move, because there's at least one parameter passed in, and again, it's always the same code. And so pop EBP, push, move, pop, and now, oh my goodness, look at that, 16. And that's because I have 4 parameters I passed in, and to unwind this stack, once I get here, I have to unwind 16 extra bytes to get rid of all of that when I'm done. So this is the bread part of our sandwich. So that's a pretty good starting point for the rest. Now that's solid, and as long as our formula does not change, as long as this function does not change the number of parameters, then, and the number of local variables. Oh yes, local variables then also, 1, 2. There's 2 local variables, so I do a sub ESP comma 8. Again, 4 each, so that's 8 bytes. And then down here, I'm going to add it on the way back. So sorry about that. I completely blanked on that. Here, this takes care of parameters. This takes care of local variables. And so now what do we have? I have the 2, the 3, the 1, the -5. I've got the return address, whatever that was from the call. I've got the EBP, and this is where EBP is pointing to. And now I have D and E, and so because I subtracted off, And now that it's time to do actual work, this is what the stack looks like. So EBP minus 8 is this, minus 12, minus 16, minus 20. Crazy, right? EBP minus 4 is the D value. EBP minus 8 is my E value. So six variables sitting on the stack, and we're not using any registers right now to do any of that work. It's all sitting in RAM. Because could you imagine trying to maintain all 6 of these things while trying to do actual operations? This would just become an insanity. So, all right, so next page is how to do, let's just focus on the actual work. So let's see what we've got. So the first line, int D equals A times X. Oh goodness, okay. So let's start. Let's take A. A we talked about is this one right here. So this is EBP plus 4, 8, 12, 16. And let's move that into the EAX register because we need the EAX register to do the multiplication. So the 3 goes into the EAX register. Fair enough, right? And so now I do an IMUL with EBP plus 20. Holy cow, right? So I go plus 20. That's a crazy number. So EBP, so plus 4, 8, 12, 16, 20. That's the X value, right? 3 is A, 2 is X. So I multiply 3 times 2 to get 6. 6 is stored in EAX. And then remember the EDX register is modified too. We'll come back to that in a little bit. And then that's done, and I do it again because I'm squaring it, right? So let's just multiply it by EBP plus 20 again. That gets me 12. And then so it's 3 times 2 times 2 is 12. 12 gets put into EBP minus 4, which we've discussed here is the D, EBP minus 4, that's D. So what did we do here, right? Local variable we set up, we took A, multiply, moved it into D. So that's 4 lines of code to do this 1 line of code in C++. So it's just now kind of, we're doing more variations of this. So now I'm going to take B times X, a little simpler than the first one, and put it into E, which is a little different variable here. So B is at EBP minus 4, 8, 12, right? That's what this is. Move it into EAX. Do an IMUL with X. We've already established X is EBP plus 20. So then, yeah, all here. So we're just taking 1 times 2. And we're taking that and the value comes out as 2, and we're putting that value into EBP minus 8, which is the E value, right? E is getting the result and storing the result in there. So now we've done all the multiplications. We're done with all the multiplications, and now it's just a matter of now setting this up and just saying, okay, now with everything blown out, EAX needs to be our return value. So let me just say, let me take D, which is EBP minus 4, move it into EAX. Let's take E, which is at EBP minus 8. Let's add that in. And then let's take the, which one is it? We'll take C. We haven't used it yet, which is at EBP plus 8. And we add that in as well. And now everybody's happy. We've done the work. The EAX register holds the result, the 9 that we were expecting from before. Because don't hold me to this. I believe it was 12 plus 2 minus 5. Is 9. Okay, so that handles, well, I've been in the way the whole time. Oh well, I can't stop this now. Okay, sorry about that. But anyway, so moving on. If you want me to send a slide, I can email you a slide. Just email it. Okay, so but that's how the actual work goes. So then now tying it all together, I think it's the final slide, is this was from earlier. This was the push and pop syndrome here. We push and pop conundrums here. And then the code, so I basically just jammed everything together. Now this is the second to last slide, but there's still one step more to do. And I said, leave the spaces here, however, like I said, sometimes, but we have to go back and enter every register that we modified that was not EAX, because we don't want to touch EAX because that holds the correct result. But anything else that's been touched by this needs to be pushed and popped after the sub and before the add. Push here, pop here. And now again, you have to understand your operations, because you look at this and you go EAX and nothing and nothing and nothing. This doesn't count. EAX, nothing and nothing, and EAX, EAX, EAX. And you would swear and swear and swear and swear that you don't have to add anything to that. But because of the way the IMUL works, the EDX register was blown out by the result, the product of the multiplication. So the final step here, we finally have it complete. All I did here was add a push EDX and a pop EDX. Again, after the subtraction and before the addition. And now every other register is put back how it is. EBP is taken care of by all of this we've been doing. ESP is all automatic because of the way the return and everything works out. But the other 6 registers, or the other 5, I guess, EBX, ECX, EDX, ESI, and EDI, all 5 of those are back to what they were because we only used the EDX in the process of creating this formula function. So that covers that. Listen, now it's hard. I mean, it's challenging. There's a lot of steps involved here, but once you've done this a few times, it really does get easier. And I really hope that when final comes, it's just a matter of you just chug it out, slam it, nail it, get your A, and run out of here, right? So I really hope that that's the case. Okay, so yep, that's it for this. Hey, look at that! I finally got an animation going. Don't have my coat with me. I am too busy to go get that coat. So anyway, so as always, swardb@cod.edu is my email address. Sending me an email. Again, coming back, how many other times did my beautiful, beautiful face for radio get in the way of everything? Quite a few, apparently. Sorry about that, but just the way things go. Those of you who don't have my PowerPoints, if you'd like them, email me at swardb@cod.edu, and I can get back to you and get you those slides so that you can use them if you so need them. But anyone, send a comment through YouTube if you don't want to email me, if you have questions or comments about that. But of course, never sit on your questions. This stuff needs practice. You need to just try it, work it out. Success through failure, and that was basically all of my undergrad, was just success through failure. All of my pre-med work, success through failure. So you can do it, I can do it, you can do it. And but if you need help, don't bat your head against the wall. Send me a question, and I'll help you out. So, okay, next video starts out immediately with doing more examples. And so, like, it's one of those, I don't know how long this video, I never keep track of how long, maybe a half hour, 45 minutes, an hour. But if you want to push right into the first part of the next one, and we go through 5 different examples, 5 more examples that get more and more challenging with the variables and the local variables and the parameter passing. So anyway, thanks for sticking with it. Have a great day, everyone. See you next time.